Okay, welcome everyone to the session. We have a number of very interesting talks for this last session of the day. My name is George Heald from CSIRO here in Perth. Our first speaker is Patrick Yates-Jones, who will tell us about the dynamics and radio properties of AGN jets in complex environments. Patrick, if you want to go ahead and share your screen. As noted, I'll give you a 2-minute warning before the question period. Thanks, Patrick. Over to you.
Fantastic. Thank you very much. All right. Hi, everyone. My name is Patrick Yates-Jones, and I am a PhD student at the University of Tasmania. In this talk, I'm going to present some work from my PhD, where I looked at the interactions between AGN jets and their surrounding environments. I'm going to start by introducing the important role these jets play in galaxy formation and evolution. Then I'm going to talk briefly about a model I developed, which can be used to calculate the spectral evolution in simulated radio sources. And finally, I'm going to finish by introducing the CosmoDRAGON project, which is a suite of simulated double-lobed radio AGN in cosmological environments, which we're working on at the moment. So first of all, let me briefly describe the role that AGN play in galaxy formation and evolution by way of feedback, and hopefully motivate why it's important that we understand it. So we know that feedback is a key ingredient in galaxy formation and evolution models, and it's required to offset the cooling within the centers of gravitational wells. We also know that active galactic nuclei, or AGN, are a likely source of this required feedback at low redshifts, and this injection of energy is incorporated into existing modern galaxy formation simulations. So here, the movie that's playing on the slide, hopefully it comes through okay. We're looking at the temperature evolution in the illustrious and illustrious TNG simulations, where illustrious TNG is one of the state-of-the-art cosmological simulations. The prescription for AGN feedback in these simulations is to inject either thermal or directed kinetic energy into the environment. These are part of the localized increases in temperature, which we see as the red-orange blasts in the movie. While this is a good approximation for how AGN inject energy into their surroundings, in reality, more complex processes are occurring. The kinetic mode of AGN feedback is driven by radio jets, which, as we'll see, have complex dynamics that impact the location of the feedback. Hopefully, by the end of this talk, I'll have convinced you that simulations of AGN jets are essential to understanding feedback processes, which in turn is necessary for proper modeling of galaxy evolution. First, just briefly about the radio jets themselves. The radio jets consist of superheated plasma that is launched from the accretion disk surrounding a black hole at relativistic speeds. This plasma can inflate huge radio lobes that can be larger than 1 megaparsec in diameter. So these are enormous structures. The radio lobes in the picture on the slide are only 10 kiloparsecs from the core, and they are the inner lobes of Centaurus A. The outer lobes of Centaurus A are up to 300 kiloparsecs from the core, but they're not shown here. We observe radio lobes with, as the name suggests, radio telescopes due to the synchrotron radiation that's emitted when particles are accelerated at the termination shock and in the lobes. And we also see X-ray emission emitted from them, both due to synchrotron radiation and inverse Compton scattering in the lobes. So there's a lot of data in radio wavelengths that we can get by observing these jet structures. And these jets and lobes play an important role, as I mentioned, in the feedback process. They sweep up environment gas as they propagate through the galaxy, and they send shocks through the galaxy, which affects star formation rates. In doing so, they transfer energy to the environment, and they stimulate mixing and circulation of gas and play a large role in the heating and cooling process of AGN. So, how do we study them? Well, we can run hydrodynamic simulations of these radio jets to explore how they deliver energy to the surrounding medium. And this has been carried out for the past 30 or 40 years. It's a well studied field. Lots of people have done these simulations. However, we need a way to map the hydrodynamic variables from the simulations to radio properties in order to properly compare with observations. So as part of my PhD, I have developed a model for resolved spectral evolution in simulated radio sources, which uses Lagrangian tracer particles injected with the jet, and these are advected along with the fluid. This model is based off the RAYS semi-analytic model by Ross Turner and incorporates a lot of his iterative Lorentz factor evolution. So that's the equation that you can see in the top right of the screen there. I won't go into it in too much detail, but the overall methodology is that each particle is taken to represent an ensemble of electrons that move with the fluid. And then the pressure and density history of each particle is used to determine the adiabatic and radiative losses for the associated electron population. So this is done with an iterative process by taking the Lorentz factor required for emission at the chosen frequency at the current time, and then evolving this back in time, including losses, to determine the necessary Lorentz factor required by the particle when it was injected, when the electron population was initialized, essentially. And in doing this, if an electron population cannot be emitting because the losses are too large for the given frequency or given energy, then we get an injected Lorentz factor that goes to infinity. And this means that we can't observe any emission from that specific batch of particles at that frequency, and so we discount it. Once we do this, the emissivity associated with each tracer particle is calculated, and a surface brightness map is produced by integrating particle emissivities onto an observing grid. So this model is really neat because it allows us to take a purely hydrodynamic simulation, which we can see in the left panel of the figure here, where we're just looking at the density. We've got the particles in the center panel, and these are tracking shocks within the jet structure and particle age and histories. And then if we go to the next slide, we can turn these into surface brightness maps for any frequency and any redshift that we want. And these are including both adiabatic and radiative losses now for our synchrotron emission. So the color maps here are showing a synthetic 1.4 gigahertz surface brightness map for increasing redshifts, including adiabatic and radiative losses. And we've got two simulations here. The top simulation is launched from the center of a cluster-like environment, while the bottom simulation is actually offset from the center of the same environment by 144 kiloparsecs. In both of these figures, the environment is marked with the environment center is marked as a location of the red cross in the last panel. So we can see that we produce something like an FR2 morphology with this approach. We have a bright region near the tips of the lobes that's reminiscent of FR2 hotspots. We see that the surface brightness decreases towards the center, which is indicative of older populations of electrons. And at higher redshifts, we see that the observed source morphology is actually changing due to increased inverse Compton losses. But we can go one step further. We can calculate the spectral curvature for any frequency that we want. So in this case, I've chosen low, medium, and high observing frequencies corresponding to 150 megahertz, 1.4 gigahertz, and 9 gigahertz. Here, a large spectral curvature indicates that the local spectrum is steeper at high frequencies, while 0 means that it is a power law with constant slope. So as we expect for an active high power radio source, there is little to no spectral curvature near the ends of the lobes for low redshifts. However, the spectrum starts to steepen around the equatorial region, which is indicative of an older population of electrons. Okay, so we've got this model that lets us take our simulation and produce radio observations from it. What can we do with it? Well, it turns out that environment plays a really important role in how radio jets evolve and the morphology that they take on. So here in the slide, I'm showing two quintessential AGM morphology types. We've got FR1s and FR2s on the left and the right. And these differences are driven by the environment into which these radio sources are propagating. So with that in mind, I'd also like to introduce the CosmoDRAGON project, where we are producing a suite of simulated double-lobe radio AGN in cosmological environments taken from cosmological simulations. So we're sampling a lot of different environments, and we're going to produce essentially a suite of simulations that we can then look at and study how exactly the environment is affecting the jet evolution. So this is an example of one of the environments that we've looked at. We've taken a cosmological simulation that was simulated using Gadget. We've picked out a subhalo and we've regridded it onto a Cartesian grid for our grid-based simulation code. And then we've gone ahead and run some jets in it. So I'm just going to show a sample of simulations that will be in the full suite. We simulate a range of kinetic jet powers, typical of both low and medium to high power radio sources, along with several velocities and several jet half opening angles. On the left figure in this slide, I'm showing 4 sources that have produced a sort of an FR2-like morphology. So these have been fast jets, so supersonic and or strongly relativistic. And this is at a single snapshot in time, as indicated on the figure. On the right, I'm showing mid-plane density slices for slow jets, which are expected to produce FR1-like morphology. And here I'm showing it at 4 different times. So at 10 million years, 50 million years, 100 million years, and 200. And the important thing here is that at 100 million years, the jet is actually switched off. And so between 100 and 200 million years, we're seeing the remnant evolution of these FR1s.
2 minutes, Patrick.
Yeah, thanks. As I mentioned before, we can do these nice hydrodynamic simulations, but we need to make radio images of them to compare them to observations. So using the particle method, the praise method that I introduced earlier, I've gone ahead and created 1.4 gigahertz surface brightness evolution movies for the 4 fast jets at a redshift of 0.05. So again, these are including adiabatic and radiative loss processes in the emitting electrons. The different jet parameters are producing different radio lobe shapes. However, we can see that they all vaguely resemble an FR2 morphology, which is reflected in the underlying cocoons we saw on the previous slide. We see that the surface brightness magnitude changes significantly over the lifetime of all sources, and we see bright regions at the tips of the lobes for the first 3 sources that could be identified as FR2 hotspots. Finally, I'll show the same thing but for the slower jets. So these are the ones that are likely to produce FR1s, and as we see, we get a clear flaring morphology reminiscent of FR1s. Interestingly, for a given surface brightness limit, you might see only part of the lobe as predicted by semi-analytic models. So here we can see all of the lobes due to the surface brightness limit that I've chosen, but you can easily see where you would start to see less of the source and measure it as being smaller than it actually is. Also in this movies, the remnant phase is shown, so we can see that once the jet switches off, the flaring region rapidly fades from the core outwards as the inflated lobes begin to rise buoyantly. Okay, so what does all of that mean? Well, modeling spectral evolution is really important. We need that to produce realistic radio properties from hydrodynamic simulations, which we need to compare with observations. And also, this CosmoDRAGON project is going to explore the jet environment interaction, which we know plays a significant role in the dynamics and radio properties, and this will provide us with a suite of simulations to explore that. And finally, in the last 2 slides, we saw that the lower power jets, for example, the FR1s, and also the remnant lobes are most impacted by the environment. I might have gone too fast to cover that properly, but that's, yeah, it's there. Thank you.
Excellent. Thanks a lot, Patrick, and thanks for the very nice graphics and visualizations there.
I hope they came through.
There's quite a number of questions in the Slack that we don't have time for, not for all of them, I mean, but there's one question that had a couple of upvotes, so I'll ask you that one, which is whether you apply jet orientation effects in your models, because that can confuse environmental effects.
Yes. So at the moment, all of the radio surface brightness maps that I've shown were with the jet in the plane of the sky. But I have looked at different orientation angles for the jets with respect to the observer and have produced some surface brightness maps of that as well. And yes, you're absolutely right. That definitely complicates things quite a lot. But I think some of the larger scale morphology changes driven by the environment are still visible. That's sort of independent of the viewing angle, as it were. But that's an excellent point.
Okay, thanks again, Patrick. I'm afraid we're going to have to move on, but let me just encourage you to go into Slack and check out the number of questions that you've got for you on your talk there.
Will do.
So thanks again, Patrick. Next up, we have Emily Kerrison, who will tell us about sea fog, tracing H1 and X-ray absorption in obscured AGM. Emily, if you could start up your slides as well.
Yeah.
It's an excellent acronym, by the way.
I can't lay claim to it, but thank you.
I'll give you a 2-minute warning before the question period starts. Over to you, Emily. Thanks.
Great. Thanks very much, George. So, hi, everyone. I'm Emily. Hopefully you can see my slides. I'm an honours student at the University of Sydney and the CSIRO. And today I'm going to be talking about my work as part of CFOG, a project on eROSITA and flash obscured galaxies. So first of all, obscured galaxies are a pretty broad class of object, but I'm interested in obscured AGN in particular and what we can learn about these from absorption studies. So when I say obscured, I mean that these objects are covered either partially or fully by either associated or intervening dust and gas. And I'm interested in AGN because typically they're very bright and they're very broad emitters across the electromagnetic spectrum. In particular, as you can see from this figure on the right, they're often made up of multiple emission components. And in addition to emission, we often see various types of absorption and subsequent re-emission in AGN spectra. And from these, we can learn things about the kinematics of the system, about its gas composition, and about what kind of AGN activity we're really seeing. So that's a little bit about the why for my talk. Now onto the what. So I'm interested in observing obscured AGN primarily through H1 and X-ray absorption. So I want to talk a little bit about those. Then I'm going to talk about some previous work that's been done connecting these two types of absorption in extragalactic sources. And in particular, I want to focus on the question of sample selection and whether this is really important for some of the results that we've already seen. Then I'm going to discuss some of the work I've been doing revisiting historic samples and making my own from the literature. And again, I want to focus on this question of selection effects. Do we see any and do they matter? Finally, I want to talk about some of the new samples that we're getting as part of CFOG, particularly using eROSITA data in the X-ray and in the radio getting data from the ASCAP Observatory project SWAG-X. Before I do that though, there are a lot of people who work on CFOG related projects, so I just want to take a moment to acknowledge them here. In particular, I'd like to acknowledge Vanessa Moss and Elaine Sadler, who are my two supervisors for the work that I'm presenting today. So now on to some discussion of absorption. As I said, I'm interested in both H1 and soft X-ray absorption. So H1 absorption in the radio is caused by an atomic transition in neutral hydrogen. And for this reason, we see this very well-defined, relatively narrow dip in the radio profile of absorbed objects. Now, this can be caused by either associated or intervening gas, but I'm more interested in the systems that are associated because that tells us a little bit more about the AGN that's being absorbed. Now, there is some evidence that we can tell from the shape of this absorption profile whether it is associated or intervening, and this also tells us a little bit about the kinematics of the gas. Most importantly, H1 absorption allows us to derive an estimate of the column density of neutral hydrogen along our line of sight. So that's one thing I'm interested in. The other is soft X-ray absorption. And this has to be associated with the system due to the temperatures involved. We don't think it's due to any kind of atomic process. Well, we know it's not. Rather, we think it's due to either accretion onto the black hole or possibly the interaction of the AGN jets with the interstellar medium. And because it's not atomic, we see this much broader turnover in the X-ray spectrum of absorbed objects, where we get much lower fluxes in this soft X-ray regime down here in this figure on the right. From this kind of absorption, we can derive an estimate of the total hydrogen column density along the line of sight. Now, perhaps naively, you'd expect the total hydrogen column density to be greater than that of neutral hydrogen along any given line of sight, and that is indeed what we see. But often these can differ by up to an order of magnitude or more. So recently, Harvey List has done some great work on trying to make these two estimates more consistent when they're derived from each method. And that's really helpful because that basically helps us to determine whether or not we're looking at gas that is co-located in each absorption process. And that leads nicely into some of the previous work that's been done connecting H1 and X-ray absorption. So what I hope are all of the relevant papers are listed down the bottom of this slide. And basically all of these show that there is a positive correlation between the column density of neutral hydrogen derived from H1 absorption and the column density of all hydrogen derived from soft X-ray absorption in obscured AGM. Now this correlation is seen in this figure on the right, shown by the red line, but you can probably tell just from looking at the graph that the correlation is pretty weak. There's a lot of scatter and a lot of these points here are only upper limits. Other things to note about previous work is a lot of these works use quite small samples of only about 20 sources or so. Some only use like as few as 4 or 5 sources. And in addition to that, a lot of these samples are selected to be what are known as peak spectrum radio sources to begin with. To my knowledge, Vanessa Moss's work from 2017 is one of the few papers that doesn't select sources in this way. And so I'll talk a little bit more about that in a minute. But first, I just want to sort of go over why these peak spectrum sources are so attractive for absorption studies. So historically, there were a number of different peak spectrum sources. There was the CSS category and the GPS category. But basically, these all amount to the same thing and they just exist along one spectrum. So now it's a lot more common to refer to them collectively as peak spectrum. And the name is quite unimaginative. It just means that the radio spectrum is peaked, somewhere between about 30 megahertz and 10 gigahertz. And these sources are also quite small. They have a linear diameter of less than about 15 kiloparsecs. In terms of optical counterparts, these can either be galaxies or quasars, but the reason that they're so attractive for studies of absorption is that these are typically very compact and very radio bright, and they're also multi-wavelength emitters. So all of that just means that we're much more likely to see any H1 absorption if it's there to see. But as I said, Vanessa Moss's work was just about the only one that I can find that didn't select its sample to be peak spectrum from the outset. So in that, there were 94 radio sources which had all previously been searched from H1 absorption and which were collected from the literature. And these all also had detections in the X-ray from XMM Newton's data release 4. Of these, 20 were known to be H1 absorbers and 74 were non-detections. And as you can see from this figure on the right, the known absorbers, for which the median flux value is shown in red, definitely have a more soft X-ray absorption than do the non-absorbers shown in blue. But because this sample was compiled from the literature, it is possible that it inherited some sort of selection effects or biases from all the surveys that came before. And so that's really where my work comes in here. So I've been trying to work out the proportions of peak spectrum sources in historic samples like this and trying to work out if it's really due to them that we're seeing this correlation between H1 and X-ray absorption, or whether it's a characteristic of the broader radio population. So the first thing I've done is I've tried to build my own historic sample. So I've taken the sample from Moss, which is made up of 94 historic sources and an additional 5 sources that were searched for H1 absorption for the first time in that paper. And I've added to that 70 sources which were compiled from the literature by Kaur and Whiting in 2010. And the reason I've combined these two is that the Moss sample was X-ray selected, whereas the Kaur and Whiting sample wasn't. So this is just another way for me to try and minimize any sort of selection effects that are going on. And as you can see from these two sky plots on the right, when you combine these two samples, they're pretty evenly distributed across the sky, which is probably a good indication that we're heading towards something with minimal selection effects. As I've mentioned, both of these surveys or both of these collections of sources were interested in H1 absorption, so every source had already been searched for it. Now, what I really want to ask with this historic sample is how many of these are peaked and also how many exhibit various kinds of absorption, how many exhibit H1 and soft X-ray absorption. But to answer these questions, I had to work out first how many sources are peaked. The Moss sample didn't include classifications, and although the Kaur and Whiting sample did, these were drawn from very inhomogeneous sources. So I had two alternatives. I tried first just looking at the NED classifications, but these were also very, very inhomogeneous. So then I did some of my own radio SED fitting using some code kindly provided by James Allison. And so what I did is I took for each source all of the photometry listed in NED below 100 gigahertz. I also added these additional surveys to that which probe lower frequency ranges. Then for each source, I fitted 2 different profiles as shown here on the right. And if one of these was a good fit to the data, I called that source peaked. Once I'd done this, I was able to look at the proportions of my historic sample. So as you can see from the numbers on the left here, the literature would suggest that peak spectrum sources are between about 30% at the top end of all radio sources, right down to possibly only 4.5%, depending on the frequency of your sample. Now, straight away, you can see that my historic sample doesn't have proportions anything like that. Just over 50% of the sources are peak spectrum. So that means when we're looking at subsets of this historic sample, say the one right down on the right that is both X-ray and H1 absorbed, it's really difficult to conclude whether this correlation between H1 and X-ray absorption exists only in peak spectrum sources or whether it's a characteristic of the broader radio population. So this is where some of the new data from CFOG comes in. CFOG is an ongoing collaboration between the AAL and eROSITA DE, and hopefully it will be a precursor to future SKA and Athena synergy. The aim of this project is to provide an unbiased and untargeted sample in both radio and the X-ray. So in the radio, it's making use of data from the ASCAP flash survey, and in the X-ray, we're using eROSITA. Now, why do these surveys work so well together? Well, the flash survey is a survey of the entire southern sky. We aim to pick up about 150,000 sources brighter than 50 millijansky in the radio. And everything's going to be imaged at 20 arcseconds resolution. So we expect to detect hundreds of H1 absorbers. I won't go too much into this because Hayden is going to give a fantastic talk about this tomorrow. So you should check that out if you want to learn more. But this works really well with eROSITA because it's a very similar angular resolution. eROSITA is going to image the entire sky at about 15 to 30 arcseconds. And it's going to have very similar energy bands to what we see in XMM Newton. So what can we learn from a combination of these two surveys? Well, it'll allow us to probe the connection between radio AGN with and without X-rays and learn something about how their emission mechanisms differ. It'll also allow us to ask and answer questions about what kind of galaxies have radio AGN, X-ray AGN, H1 absorption, and X-ray absorption. In terms of what I'm interested in, it will allow us to trace the column density of all hydrogen and neutral hydrogen for a very large sample, hundreds of galaxies. A sample so large that we've never really been able to do that before. And it'll also be able to give us a better handle on the true fraction of peak spectrum sources and indeed peak spectrum absorbers across the entire sky. Of course, Flash and eROSITA are still in the process of collecting data. So at the moment, I'm using lots of data from the SWAG-X Observatory project. So this is imaging the field that is covered by the gamma-9 field in the optical and the EFEDS field, which is the test field for eROSITA, shown in yellow on this figure on the right. So this field is imaged at between 10 and 20 arcseconds resolution in the radio. And with ASCAP, we're going to be sensitive to any H1 absorption lines of a redshift less than about 1. So already we've got some continuum data that's been released on CASDA, and the release notes have already been circulated. So if anyone's using this for science, we'd love to hear feedback on it, especially if you find any issues. But in terms of my project, what's really interesting is that we already have almost 6,500 sources that are brighter than 10 millijanskys in this tiny area. Well, it's not tiny, but it's much smaller than we're going to have eventually.
2 minutes, Emily. Great,
thank you. In addition to that, we're going to have lots of data coming out very soon. So the SWAG-X field is also being imaged in 2 bands, SWAG-X low and SWAG-X high, the details of which you can see on this slide. We'll be releasing continuum and spectral data for the entire field, again, sensitive to H1 lines of redshift less than about 1. The observations for this were finished at the start of this year, and we're hoping it's going to be released very soon on CASDA. And this is going to be really great because it's going to provide really deep multi-wavelength support and follow-up for the EFEDS field. Even without the spectral data, though, there's a lot that we can do with this. So I've been looking at some of the continuum data and comparing it to my historic sample that I showed before. So here on the left, we've got the SWAG-X data, the radio data, and I'm comparing this to my historic sample. So on the x-axis, we've got a measure of source symmetry. On the y, we've got a measure of how resolved the sources are. As you can see, a lot of the historic samples sitting up here, they're very unresolved, but the SWAG-X sample really covers a much wider parameter space here. So it'll be really interesting to see where all the H1 absorbers sit in this parameter space. On the right-hand side, we've got all the SWAG-X field cross-matched with XMM data release 9. So that's the latest release from XMM Newton. And again, we can see the colored points here, the historic sample I was looking at before, and the black points are everything that we add by looking at the SWAG-X field. So again, we're going to be able to probe a much wider parameter space to look for both H1 absorption and X-ray absorption and see the connection between these two. So next steps for my project. I'm going to be looking at the EFEDS field for SWAG-X. I want to explore some metrics for X-ray absorption because, of course, the sensitivities of this telescope are a bit different to those of XMM Newton. In terms of SWAG-X spectra, I'll be able to look for new absorbers, and I really want to be able to answer what fraction of this population of peak spectrum and what fraction of those have X-ray absorption. In terms of the longer term goals, the stuff that I'm doing now will provide a nice precursor to Flash and eROSITA synergy, which will in turn hopefully lead to great collaboration between the SK and Athena. So this is what I hope you've taken away from my talk. There is, it would seem, a correlation between H1 and X-ray absorption, but we can't tell yet from historic samples whether this is stronger for peak spectrum sources or whether it exists in them alone. It's very possible that what we're looking at the moment is affected by selection bias. However, the good news is with CFOG, we're going to be getting lots of new data very, very soon that will provide an unbiased sample and allow us to ask and answer questions about the true fractions of the radio population that are absorbed and the population which has X-ray absorption or not. And I think that's about all I have time for.
Great, thanks, Emily. Thanks for that very interesting talk. We've got a question from Jess Thorne, who says, nice talk. Have you looked into the host galaxies, for instance, stellar properties, environment, etc., of the historic sample of peaked spectra and absorbed objects?
Yeah, thanks. Good question. So I've been looking at it a little bit. I've been looking at some of the, I guess, some other wavelengths to see what I can gather from them. So I've been looking at some of the WISE colors and trying to see where these things sit on like the WISE color plot. I seem to be getting a lot of galaxies that are ellipticals and some that are QSOs, but beyond that, I haven't had much of a chance to look into it yet, but it's definitely on my to-do list.
Great. Are there any questions in the room or in one of the hubs? No? In that case, I think we should move on for reasons of time, but thanks very much, Emily, again.
Thank you.
Okay, our next speaker is Christopher Onken, who will be talking about ultraluminous high redshift quasars from SkyMapper. Christopher, if you don't mind sharing your screen. Oh, good, you're on the task. Perfect. Thanks, Christopher. I'll give you a 2-minute warning. Over to you.
All right, thank you. So there are some incredibly massive black holes very early in the history of the universe, more than 1 billion solar masses, less than a gig year after the Big Bang. And with sort of standard assumptions about the growth rate for black holes, namely an Eddington ratio of 1 and a radiative efficiency of about 0.1, that implies some really massive seed black holes early in the universe. And that's led to a lot of novel theories about unusual progenitors for these black holes or alternative ways of growing them to very large masses. But of course, they didn't stop growing at redshift 6 or 7. And that brings us to SMSS J2157. So this was a luminous quasar discovered by our team in 2018, just 1.3 gigayears after the Big Bang. And this is the most luminous known quasar. So it's eating about 2 solar masses worth of material every 3 days. And with some follow-up near-infrared spectroscopy that we published last year, measuring the width of the magnesium to emission line in the rest frame UV, but here redshifted out to the H band, we were able to determine the black hole mass of this object is about 34 billion solar masses. And the challenge then is to find more of these things, in particular how to distinguish between this faint red object, which is more than 40 gigaparsecs away, and this faint red object, which is a star less than 300 parsecs. And in fact, there's nearly 2 million SkyMapper DR3 sources that are as red as J2157. But fortunately, we now live in the era of Gaia, and we can separate the many, many foreground Milky Way stars from the background sources like quasars. And so combining the astrometry from Gaia with some very simple color cuts from Gaia, we can eliminate a vast number of the potential contaminants. But it's not quite that easy. We can't just go out and immediately find all of the distant quasars, because it turns out that beyond redshift sort of 5.5, there's almost no known quasars that have Gaia parallax measurements. And that's pretty easy to understand. It's because the Gaia astrometry uses the G-band filter. And as you can see on the right-hand side, when you get to redshifts of 5.5 and higher, there's very little flux making it onto the G-band detectors. And so as we scale from sort of redshift 5.7 up to redshift 6.4, there's almost no light making it onto Gaia's astrometric cameras. And so we'll need to temper our expectations about the quasars we can find, but as long as we focus on slightly lower redshifts, we should be able to do pretty well. And in fact, we've designed some very inclusive selection criteria to make sure we're not being overly biased from previous studies of high redshift quasars in order to conduct a search that will find almost all of the quasars in useful redshift range. And so by combining the optical data from SkyMapper and from Gaia, near-infrared data from some of the large-scale near-infrared surveys in the Southern Hemisphere, and mid-infrared data from WISE, we can narrow this down to less than 200 candidates with a Z-band magnitude brighter than 18.6. And so we take all of these things and we funnel them into the ANU 2.3 meter. Now, if you're going to conduct a large-scale program over many years, it is incredibly valuable to have dedicated graduate students like Jack Hahn and collaborators in Europe like Patrick Tisserand, who are willing to help out with much of the observing. And what you often get when you take all of these source catalogs and feed them into the WISE IFU instrument is a number of contaminants, of course. So some of these contaminants are just distant M giants, so they don't have much parallax of proper motion. And you can see here on the top, there's the black WISE spectrum and in the red spectral template. And so you can see that's a pretty good match for an M giant. And in the bottom, we have a very unusual class of object known as an Ophiolo ball. So this is where there's so much absorption from iron and magnesium that there's almost no light shortward of the magnesium line, and it can replicate the same kind of cutoff you would get at the Lyman alpha edge. And it's only by virtue of the fact that none of the other emission absorption features seem to show up or seem to align with a high redshift quasar type of spectrum that you can distinguish these things as being Ophiolo balls. And of course, if you go to rest frame optical wavelengths in the observed frame near infrared, you can see that they have normal-ish kinds of quasar spectra once you get out to sort of the rest frame optical. But after you get rid of all those contaminants, what we're left with is more than 100 new quasar discoveries. So it's 119 that we published in this newspaper, plus 21 from a paper that we published with the initial sample last year. And including some cuts on the luminosity and the redshift restrictions, we have 97 quasars from about 14,000 square degrees that we've searched in the Southern Hemisphere. Now, as I mentioned before, we have some very inclusive selection criteria. So we think that this sample is more than 90% complete, brighter than 18.6 magnitude. And so from those 157 candidates within that selection box, we have 91 high redshift quasars. We have some slightly lower redshift broad absorption line quasars. We have some stars. We have a few other objects that are lower redshift. We're not always entirely sure what they are, but they're not high redshift quasars. And then there were 5 when we submitted the paper to monthly notices that we didn't have spectra for yet. But as of a run that just finished on Monday night, we can reduce the number without spectra. We've increased 1 to each of those other categories. So we have 92 high redshift quasars from the sample of 157 candidates. So we want to compare this with what similar studies have done previously. And there was a study published in 2016 using Sloan plus the all-WISE sample from WISE, covering a very similar portion of the sky in the Northern Hemisphere over a redshift range that matches very well with ours. Now, this sample from the Sloan, they had nearly 100% spectroscopic completeness, down almost a magnitude deeper than our completeness limits. But because they didn't have Gaia available, they had to use WISE color cuts to restrict their sample and eliminate the foreground Milky Way stars. And because they couldn't get into that dense stellar core, they had to have a much more incomplete selection from the mid-infrared photometry. And so their mean completeness, they estimate to be about 60%, and it's a strong function of redshift. But even if you account for that 60% completeness, we have roughly twice as many as they would have predicted from the northern hemisphere. So we expect that there's many more objects to be found still in the north. Now we want to take this complete sample and we want to use it to estimate the quasar luminosity function. Now the luminosity function is often parameterized as a double power law, which involves 4 parameters that need to be fit. Because we're only really concerned with the bright end where we have the very high completeness, we can fit this using the cumulative counts and get a very tight constraint on the beta parameter, the bright end slope. And we see that we can measure it to be minus 3.84 at about redshift 5, which is a much tighter constraint than Yang et al. Were able to derive from the Sloan sample in the north, where they were trying to fit the individual points in each luminosity bin. And this matches well with other estimates of the bright end slope at slightly lower redshifts, for example, from recently published from Bautzi et al., also using the southern hemisphere and using SkyMapper data. And so this is a very tight constraint then on the bright end slope of the luminosity function. With this very complete sample now, we want to take the luminosities and we want to move on and try to actually estimate the black hole masses. So we've recently been granted some time on the SOAR telescope in the upcoming 2021B semester to try to measure the magnesium line in the H band for these most luminous objects in this redshift regime. And we're still waiting on the results from the X-Shooter proposal that we submitted for the same upcoming semester. So the work of trying to understand the black hole mass distribution and the mass growth over this short range and look back time is work being led by Samuel Lai, who was a graduate student who began work with us earlier this year. So he'll make what measurements he can from the magnesium 2 line. We'll complement those mass estimates with some rough estimates of the black hole masses from accretion disk models in order to understand how the growth of the black holes is occurring over this time frame. Now, we've been reporting on quasar discoveries from SkyMapper data for quite a number of years now. The screenshot on the right is from a presentation at the ASA conference in 2017, reporting redshift 4.6 quasar from the SkyMapper early data release. And we imagine that there will be future reports coming from our team. But we want to enhance the spectroscopic completeness by improving the spectroscopic coverage at deeper Z-band magnitudes. We think there are many more objects to be discovered in the north. And we think that future SkyMapper data releases will greatly improve the number of candidates at those fainter magnitudes. And in the long run, perhaps a near-infrared version of Gaia would be useful for discovering these even higher redshift objects than we're able to probe at the moment. And it's been just last month, the idea of a near-infrared astrometry mission was included as one of the things that the Voyage 2050 committee had supported through one of the recent ESA committees. And I'll be happy.
2 minutes left. Sorry for interrupting you, Christopher, as you were wrapping up. Thanks very much. Sorry for that very awkward warning just at the very end there. We've got a couple of questions on the Slack and plenty of time. The first question was from Stuart Ryder asking, oh, sorry, there is a reply to that one. Maybe it's answered already. Yes, so I'll go on to the next one, which is from Emma Ryan Weber. What lessons can be drawn from this very complete sample to help future searches for redshift greater than 6 quasars before near-infrared Gaia?
So it may be that there are missions, Euclid, for example, that may provide some of that near-infrared data on a quicker time scale than a near-infrared version of Gaia. I think it gets very hard to use the Gaia astrometry just because there's no flux available to the Gaia instrument. But there are other ways of getting the astrometric data maybe at less precision, but still hope to discard a large number of the potential contaminants in such a sample. So I think the combination of the photometric cuts that you can make on various colors, covering as wide of a regime as you can in wavelength, that with whatever information you can get on the astrometry, I think would be beneficial to improving the selection at higher redshift.
Okay, we've got a question from Mike Creel, who asks, what do you think the progenitor for that 32 billion solar mass black hole could be?
That's difficult to know. So people have proposed, primordial black holes of large masses, direct collapse of very dense material in the early universe, or I mean so the standard thin disk models break down at Eddington ratios above roughly a half. So already, once advection becomes important, your radiative efficiency can go down a lot, and you can actually grow much faster than the canonical models. So it may be that you can start from a typical seed of something, the end product of stellar evolution, and that there may be growth models that can get you to these very large masses even within a gigayear.
Okay, and one last question, if you could answer this one relatively quickly, from Brent Groves, who says, nice sample. Do you have any information about the hosts or environments about the high redshift quasars?
The short answer is no. We have not explored the environmental factors for these objects, and we've not, I guess the most detailed study is in J2157, and we were not able to detect any host galaxy against the very bright quasar in the center.
Great, that was the perfect length as well. I'm glad you didn't take the very shortest possible answer for that one. Thanks again very much, Christopher. Okay, our next speaker is Guillaume Drouart, who's, I think, right? That's why you're here. I'm just gonna pop up your slides for you and start this share. Oh my goodness, why is that happening? Could you help? Yeah, could you, this one? Yeah, okay. Yeah? I should have let you do this, sorry. So Guillaume's gonna tell us about toward the first sample of radio powerful AGM in the EOR. Do you wanna make that full screen? Yeah. Yeah, if you could do it, I'll give you a warning.
Yeah, 2 minutes?
Yep. You, Guillaume.
Okay, cool. Can you see the mouse? Like, yeah, sure. And in terms of microphone, like people, how they hear me? Just speak there. That's all right. Perfect.
We hear you.
Okay, so I will talk about I will talk about like the first sample of radio powerful AGM in EOR. That's really cool because the first 3 talks you got like is going to make me take some shortcut right at the start. So in particular, Christopher's talk is nice. Was nice because he showed you like one basically facet, like one side of the same coin, basically, which is looking at very powerful radio, a powerful AGN at the highest redshift. He already showed like one version of this diagram where one of the main interests to find AGN at the highest redshift is also to answer how the first supermassive black hole formed and how actually they evolved to be this massive in a very short time scale. This diagram is shown here is the observed quasar here, basically less than gigayear after the Big Bang. We're already 10 to the 9, 10 to the 10 solar masses. But there's this race to go in further and further redshift. And the reason for this is basically if you look at what the redshift, the correspondence in the redshift here, you see you pass the redshift 6, you enter in the OR basically. And by redshift 10, you might be able to tease some of the 2 parameters that lead basically the black hole mass you observed beyond redshift 6, which is basically the initial black hole mass and what the accretion history onto that black hole was. And by those observations, you can probably start like at least discard some of the scenarios for the most massive supermassive black hole. Now, as has been shown a bit before, a quick census of where do we stand in terms of like AGN population with redshift is basically summarized here. It's already out of date. It was in 2018, and Christopher just showed a new diagram where in the redshift 6 area, you can actually nearly double or triple the sample like from that diagram. So, at the door of the OR, we already start sampling a lot more actually active systems. And I would just highlight like a couple of very, very recent things here from like last couple of months ago, is like the most distant quasars was pushed a tiny bit further here, and 2 quasars were discovered here beyond the redshift 6.4 mark. Those 2 black lines are quasars who are detected also in radio. The thing is here as well, very important, is all these diagrams are optically selected quasars. So that means these radio thing, they were not selected for this. So they detect in radio, but they're not radio powerful at all. It just happens to be the case. Now, if you do the other exercise where, we can detect and select AGN from radio, from like, the all-sky surveys, this is what you get. We got only a few hundreds basically across the redshift range up to basically redshift 5 from two decades ago, but this record and the limits were really pushed very, very recently. Like we discovered one in 2020 that I'm going to talk about, and another one was discovered in 2018 using the TGSS survey. So this is something I would like to stress here is optically selected sample for AGN are very useful because you can use major, massive, radio survey, optical surveys and just use the Lyman break technique to find them. But however, you're sensitive to dust. If it's obscured, your flux falls and you're not able to select quasars anymore. That's where radio get into the game, because radio is dust insensitive. So you're going to catch both type 1 and type 2 AGN, unobscured and obscured one, with the same probability. And it's completely complementary there to provide many things like a complete view of the AGN duty cycles and things like that. And the radio emission on top of that with powerful jets would just provide you with environmental information, because that's ramming against the IGM or the intercrustal medium. You can also trace the past accretion history, because there is a delay compared to the optical light, which is nearly instantaneous accretion rate tracer. So this is why having like radio selected sample is so important. It's just complete this picture. And on top of that, for free, as they're very radio bright and you're going at the highest redshift, you can start looking at H1 absorption into it. So on top of that, for free, you got actually an IGM probe beyond into the UR. So now you're all excited about this, is how do we select them? So basically by how it's been made like for a long time, just with some twist, is on the right, you're seeing a radio SED with flux versus frequency. And historically, all the radio selected sample were made from the gigahertz frequency. So you take 2 major surveys, you cross-match them, derive the spectral index from the gigahertz frequency. And with the redshift effect, what you're seeing is you probing a steeper and steeper part of the SED. Therefore, by selecting the steepest sources, as they are selected here, you selected preferentially highest redshift object. And that's why radio galaxies or radio selected AGN were holding the record of the most distant object for decades. So now what we want to do is, the problem like with this technique is you start hitting your sensitivity threshold into the radio surveys. So that's why the progress to actually find even further redshift was so long and so painful, because you need basically to push the flux limit. But you can alleviate this simply by going at lower frequency, because you gain a lot of flux and you do the same kind of exercise. So that's how we design our new technique, using the MWA. And what you're seeing here is taking here the MWA data from that gray area into the SED, and plotting the spectral index you can measure, you can fit here, versus the curvature you observe into the 20 data points you have in the GLEAM, thanks to the very excellent frequency coverage of GLEAM. And what we observed is from the radio galaxies, high redshift, powerful radio galaxies into the around the redshift 4, we observe this turnover into the spectrum here. And so if you use those SEDs and you redshift in them even further, you can create those tracks onto the MWA spectral frequency versus spectral curvature, and see in which area of the diagram they're going to end. And what you realize is they're ending up in a part of the diagram which is not that dense. So by making a cut here, you're able to isolate some sources, because the main problem is those sources are rare, so you can't look at every source in the sky. So you need some quite clever trick to select them. And after we use the gamma fields with a wealth of multi-wavelength data to isolate the near-infrared faint emission. Remember what I said before, what we want is not the quasars because they are optically selected. We're going from radio and selecting like the faint in K-band means the either obscure, either very far, or as is also fully stellar emission or nearly fully stellar emission. That means they're not very massive. In any case, you're going to explore a part of the parameter space that's never been explored before. So by focusing on the gamma fields and selecting like the source which are not detected in Viking, you have like something radio bright curved and not detected in infrared. So they're all the hallmarks of something which is a high redshift. And for what we did is, as you faint in near infrared, regular near infrared spectroscopy is not going to help you. Something like HIGH-REDSHIFT would require 2 to 3 nights of integration for a single source. And as we were talking about, like many candidates, you want something cheaper. So that's why we went to something else. We're going to determine the redshift from the molecular gas emission. So rather than using your atomic gas, you're taking molecular gas. So using ALMA, integrate, and there is CO line there, and normally we give you ambiguously the redshift of your source. So we follow that with OCI to have like deeper near infrared image to detect the host location, and follow up also with ALMA to get the spectra to determine the redshift. And of the 4 candidates we selected, that's what you see. So the grayscale image are OCI, the deeper observation. The yellow cross is where the host is, and the red contours are the ALMA continuum contours. Note that those sources are like a couple of arcs across maximum. I will focus on the one on your left-hand side, where basically, like they were not detected in Viking. The host is there, no problem. There is a strong 100 GHz continuum emission, which seems to be radio, given like the morphology. And the right-hand source are basically misidentified lower redshift companion. We'll come back on those ones later. So now if you take the yellow cross, extract the ALMA spectrum here, that's what we get. And for the 2 sources on the left that I presented, that's what also you can observe, is the red circle, the red square here is highlighting the new source, which is immediately identified at redshift 5.5, because you got 2 CO lines, and that's an ambiguous solution to actually for that redshift. And a second source, which might be actually very high redshift, you can see redshift 10.15. So we get very excited 2 years ago. To make a long story short, we asked for more time. These sources are not redshift 10, so don't get too excited. But I can't resist to show you like some of the progress we made like over the past couple of years, because there's been like a long fight. And that's what you see like from a paper we recently submitted. This is the radio ACD of that source. And there is more than 40 points in the radio ACD. I think you will find like hard to find a radio source in the sky who got that much coverage. That's 3 decades nearly in frequency. So it's well detected in radio. There is no problem with that. Again, like from low far to ALMA basically. And there's a lot of like upper limits. All the triangles are like upper limits. And even more, I would just, I know it's in frequency, so near infrared astronomer, I got you, no problem. So we're going to make a bit of a flip here. We're rescaling, and that's what this source looks like in a full electromagnetic spectrum, from UV to low far. I missed the X-rays, I know. We'll have that soon, but whatever. But what we got excited is because of the new data in HST here in optical, like all those like upper limits, very stringent. You can see like the chi-square map is showing like a solution around redshift 2 to 3, which is still doable, but like I will pass the details, but it would be quite tricky to actually reproduce something like this. But we're very excited because of that line here, because we're talking about a redshift 8 point something source. So I would let 1 second for you to realize this. This SED might be the most distant active supermassive black hole we're seeing at the moment. Might be. We're still working on it. It's been like teasing us for 2 years. Maybe we'll have the answer soon, maybe not. But we're getting there. And so it works. Except for the one maybe at high redshift, there is another one at 5.5. So we already broke the record from 20 years back. So we can now actually construct a full sample actually of radio allowed AGN, radio selected AGN. And so why it's so exciting, because now there's a new sample. What I all presented to you was a pilot study where we're only on the gamma 9 field, so 50 square degrees. So those sources are rare, but if you increase, there was a demonstration of how it works. And now if you increase all that area to the Viking survey, so 20 times larger, we end up by redoing the same selection I proposed to you, even if actually more refined, because we are not having the same problem of the two low redshift misidentification we had before, we end up with 55 candidates. If you assume a 25% or 50% success rate, as we have shown with the previous, with the pilot sample, what you start finding is like we might detect about 30 objects in there above redshift 5 or 6, which is really nice. But if you take also the prediction from the S3 kit simulation, it seems to be a bit in tension. And we're going to miss objects because we're not complete, we're efficient. That's it. So already with just detecting those and confirming the redshift, it might be actually very interesting to know, have a first guess of how many radio sources there is out there at those kind of redshift. And I will just like leave here with my conclusion. Just remember, we have a new selection method, which is like working quite well. We have refined the selection criteria even further. We will actually avoid to have like some further misidentification. The application for all these radio selected sample is actually awesome. H1 absorption, AGM duty cycle, studying the host because you're obscured. Always remember this. You can study the stellar population directly compared to a normal quasar. And yeah, and also the black hole sitting, you participating to the same kind of picture. Also, something I want to stress is for this kind of object, ALMA is going to be one of our only way to determine redshift because of the faintness in the K band. I mean, when JWST will be up there, it's a different game. But for now, that's what we have. And I didn't mention a lot of things that's happening in the background. And you know, I list all the side projects and things that are happening at the moment here. So we're pretty busy. We're pretty busy right now. Thanks.
Share the microphone with you if that's okay. Thanks very much, Guillaume. There's a few questions in Slack for you to look at later. I think there's time for one. One question has an upvote, so I'm going to go with that one, which is from Kieran Lucan, who asks, what observations do you need to confirm or reject the redshift 8 AGM?
Or what you can get. So yeah, okay. So the long story here is it would be very difficult. We already like made the calculation. That would be tricky. We asked for more at the ALMA time. It didn't really work well. We could ask for even more. We tried. We have to the answer normally of the type like imminently. So let's hope for the best. Otherwise, HST. Obviously, we asked actually for time with HST with a Grism because you don't have the atmosphere, so it's a bit better. So yeah, definitely at the day of today, HST could help us for these specific objects. And we put in a proposal that we actually have accepted like a few weeks ago. Is Nick around? Yeah, there you go. When it was accepted already? Yes. Yeah, there you are. So we might have the answer with this. Otherwise, yeah, it's even more on my time, but like it's becoming a bit tricky. There.
Excellent.
Thanks.
Okay, you've got 3 other questions in Slack, so encourage you to answer those there. And thanks very much again.
Yeah, thanks.
Okay, next talk is by Shaddai, who will talk to us about the discovery of millisecond pulsars in the globular cluster omega Cen. She has started screen sharing, thank you. And I'll give you yep, I can hear you, and I'll give you a 2-minute warning. Over to you.
Yep, sounds good. Hang on. This way? Yep, all right.
Perfect.
Yep, thanks, George. Yes, my name is Shaddai, so I'm from Western Sydney University. It's great to have this opportunity to talk to everyone about pulsars in the global cluster Omega Centauri. As you can probably tell, I'm not really expert on global clusters, but I find it impossible not to actually spend some time on Omega Cen, since it's such a unique system. So here, I'm showing a Gaia sky map, and immediately Omega Cen stands out. And if we zoom in, we see this really bright, massive star cluster. And it has a really, really long list of unique characteristic features. And I'm sure many of you know better than me. But apart from optical, Omega Cen is also actually a relatively bright source in gamma ray, as you can see in this Fermi sky map, along with a few other massive clusters like 47 TAG and Fazan 5. So these very unique features of Omega Cen have led to the suggestion that it was actually the nuclear cluster of a tightly disrupted dwarf galaxy. Here I'm showing a plot from the classic Becky and Freeman paper, where through simulations, they show the star formation rate as a function of time caused by the interaction between the dwarf galaxy and the Milky Way, which I find actually quite fascinating. So there are honestly too many exciting topics about Omega Cen. And today I think I'm going to just very, very briefly touch on two, which are related to the topic today. And the first one is there an intermediate mass black hole in the center of Omega Cen? Since we speculate that it was the nuclear cluster of a dwarf galaxy, and we saw evidence of intermediate mass black holes in dwarf galaxies. So people argue there's possibly also a black hole in the center. But recent studies show that it's probably unlikely that we have a very massive intermediate mass black hole in the center of Omega Cen. But I think whether we can have actually a less massive, for example, a few hundred solar mass, a few thousand solar mass black hole in the center of Omega Cen is still an open question. Another very hot topic is about the origin of gamma ray from the core of Omega Cen. Probably everyone except pulsar astronomers believes that gamma rays are all from dark matter annihilation. Recently, actually quite a few papers show that with some dark matter annihilation models, we can perfectly explain the origin of gamma ray in the core region. But we also know, as explained by Roland in the morning, millisecond pulsars can also actually be the source of gamma ray. So again, this is an open question. And for pulsar astronomers, the biggest mystery about Omega Cen is, so where are actually the pulsars? Because we know that global clusters are the best place to search for millisecond pulsars. For massive clusters like 47 TAG, we say it holds like close to 30 millisecond pulsars. So it's really confusing and hard to understand why we didn't find any pulsars in Omega Cen. So we decided to revisit Omega Cen in 2019. This is largely motivated by the installation of the new ultra-wideband low receiver at Parkes. So the idea is that with this ultra-wide frequency coverage, we can on the one hand probe steep spectrum sources, which effectively increase our sensitivity, and on the other hand, we can go to high frequencies to search for binary system, which could be in, for example, eclipsing systems, and with high frequencies, we can get away from the eclipsing. While the data processing of such a wideband is really challenging, it turned out to be rewarding because we finally discovered some pulsars in Omega Cen. So our first observation reviewed pulsar A and B, and our follow-up observations enable us to find another 3 pulsars. So this is the first 5 pulsars we published in the paper last year. And 4 of them, A, C, D, and E, are isolated pulsars, and pulsar B is in a compact binary with a very low mass companion. And it turned out that pulsar B itself is also very interesting because it's the first irregular eclipsing black widow pulsars. I probably don't have time to go into details about this pulsar, but I will come back to the pulsar population later in the talk because they look a bit weird. We also managed to pin down the position of all these pulsars. Here I'm showing a compact array 2.1 gigahertz image of the core of the cluster. And you can see all 5 pulsars published so far are within the core region of the cluster. 3 of them are associated with X-ray sources. There are a few more compact radio sources, and they could be pulsars to be discovered. But I think it's quite interesting to see that the radio map of the core of Omega Cen is so empty. If you're thinking about how dense the cluster is. So since then, we have been monitoring Omega Cen with parks. We managed to find some more new pulsars, and we are also working on low frequencies with GMRT and try to find some more steep spectrum pulsars in a cluster. Right. So that's the discovery of the pulsar. What I find more interesting is actually about what the pulsars actually can tell us about the cluster. You probably know that the ultimate weapon of pulsar astronomers is pulsar timing, because we can measure the spin period of pulsars so precisely, even very small perturbations of the spin period, for example, from the gravitational potential of the cluster or even a black hole can be reviewed through the pulsar timing. So we can really do very interesting science. So here I'm showing the first 2 years of timing of 5 pulsars we have already published. And while they are very weak pulsars, we do show that actually they are very stable and they can be actually very good high precision timing pulsars. So one thing we can immediately do is to search for the pulsation in gamma ray. So here I'm showing you the significance of pulsation in gamma ray as we accumulate more and more photons with Fermi through its lifetime. We haven't detected any significant pulsation in gamma ray yet, but we suspect that's because of the limited timing baseline we have at the moment. We only have 2 years of timing baseline, while the lifetime of Fermi is 13 years. So we expect with more parks timing data, we will be able to eventually review the gamma ray pulsation and then tell the actual origin of the gamma ray. And as I just mentioned, with pulsar timing, we can really measure the spin period of pulsars precisely. And through the precise measurement of the line of sight acceleration, we can actually probe the gravitational potential of the cluster. So on the left is one example that people have done with 47 TAC, because we know where the pulsars are, and then we can measure the acceleration and compare them with models of the cluster. Obviously, for Omega Cen, we need more pulsars. And I think eventually we also need more realistic models of the cluster in order to actually do this kind of exercise. So that's definitely something I would like to talk with experts on the cluster. And finally, I would like to actually talk about the formation and evolution of pulsars in Omega Cen. So one thing you can probably immediately tell is that the pulsars we discovered so far are very, very weak. So they have very low luminosity. So although we only have 6, 7 pulsars known so far, it's already difficult to understand actually with the known luminosity function of radio pulsars. And then another very interesting point is we have much more isolated pulsars than the pulsars in binaries. So we have like about 6 isolated pulsars and only one pulsar in binary systems. So yeah, thanks. So here on the left, I'm showing a plot of the core radius of clusters versus the core surface luminosity density. And I plotted all clusters with more than 5 pulsars on here. And all the red points have more isolated pulsars than binary pulsars. And blue points have more binaries than isolated pulsars. And for the red dots, the larger it is, the higher the isolated pulsar fraction is. And for the blue, the larger it is, the higher the binary fraction it has. And the dashed lines I'm showing here is the so-called gamma parameter, which characterize the encounter rate per source in the cluster. So you can see that all the clusters with more isolated pulsars tend to have very large gamma, while pulsars with more binary system have much smaller gamma. And the theory is for systems with very large gamma or high encounter rate per source, this binary system were disrupted during the evolution. So that perfectly explains this distribution of clusters. But you also notice that omega sen, which has very low gamma, is actually sitting in the bottom right corner, miles away from all the other clusters with large gamma factor. So what's going on here? So do they have different formation evolution history, or are we missing a lot of binaries in omega sen? I think that's something we need to understand. So I think that's all I want to say. So finally we find the population of pulsars in omega sen, but they look a bit weird, and it will be really interesting if we can understand their formation and evolution in the context of the evolution history of omega sen. Yep, that's all. I'll stop here.
Excellent, thanks, Joe. Excellent. Okay, we've got time for one question from Marcus Lower. Very cool discoveries. Are there any plans to perform searches for additional new pulsars in omega sen with MeerKAT?
Yes, good question. So you probably know that we cannot actually propose like the pulsar, the transient projects are not actually open for everyone to propose. So I do know that omega sen is on the top of their list, and with the sensitivity of MeerKAT, I believe there will be more pulsars being discovered in the near future. Yeah.
Excellent. Okay. Well, I think we should move on due to time, but thanks very much, Shep.
Thank you.
Okay, and oh, sorry, do you just share? Yeah. Yeah. Our final presentation for today is by Dilpreet. Kaur, did I pronounce that right? Yeah. Great, excellent. Who will tell us about, sorry, I've lost your title, detection of chromatic dispersion measured towards the millisecond pulsar J2241, etc. So once this gets sorted out, so I'll give you 2 warning. Yeah.
Hi everyone. So I'm Dilpreet. I'm a recent PhD from Curtin. I submitted my thesis last week. So today I'm going to present one of the very important results from my PhD research, which is the detection of chromatic dispersion measured towards this millisecond pulsar. So millisecond pulsars are known as highly stable clocks of the universe, and pulsar timing array experiments, taking advantage of that, and having an array of millisecond pulsars spread throughout the sky and getting their time of arrivals very precisely with the aim to detect low frequency gravitational waves. So there are multiple different groups around the world who are working on this. And for example, North American Nanograph Group, Parkes Pulsar Timing Array Group, European Pulsar Timing Array Group, and also there are some newly emerging groups from India, China, and South Africa with the ultimate goal of detecting low frequency gravitational waves. And this is also a key science area for SKA. So this is a long-term project and it comes up with lots of challenges. So one of them is doing the interstellar medium corrections. So you have already seen that what is dispersion. So measuring the dispersion measure is very important in the PTA context. So for the PTA, they need to measure and correct for it for every single observation, for every single target in the sample. And there are multiple different groups who are like continuously working in this area. But so here I'm showing you just one example of this is 1909, one of the best timed pulsar from the PTA sample. You can see that there are some DM variations. So they vary from few parts in 10,000 to few parts in 100,000, but they look very small, but they can induce a timing delay of 300 nanoseconds to the PTA sample, which is the kind of precision they are already going to want to achieve to detect the ultra low frequency gravitational waves. So if they have the noise of 300 nanoseconds, how can they detect the gravitational waves? So it's very important to measure it, but it's very hard because it's just 300 nanoseconds. It's very hard to measure. But as the dispersion varies as the has an inverse dependency with the frequency, the same delay can produce 30 microsecond of delay at the low frequencies. So for the low frequency observations, we have the MWA. So I'm just showcasing one of my art. So we all know it works from 80 to 300 megahertz. It has 256 tiles, but we can only use 128 at a time. And it it gives us 30 megahertz of bandwidth. So I'll tell you that the MWA was not originally designed as a pulsar instrument, but we can do pulsar science with the MWA with the help of this VCS system, which is voltage capture system. It records the voltages from 128 tiles with the frequency and time resolution of 10 kilohertz and 100 microsecond. The data rates are very high, so we cannot process it on site. So we take everything to the POSI supercomputing center. And there we can beamform the data either with the native 100 microsecond of time resolution, or we can also use the higher time resolution of 8 microsecond, which is very important for the study of millisecond pulsars. So as I told you, the MWA gives us 30 megahertz of bandwidth, which we can use anywhere from 80 to 300 megahertz. But we have also the flexibility that we can split this 30 megahertz into multiple different channels and then spread it across the entire frequency range. Why we are doing it? Because this gives us the larger frequency live around, and this is very useful to study the ISM effects, especially at low frequencies. So here I'm just showing you one of my results. So by using the larger frequency lever arm at low frequencies, and we can able to achieve 1 microsecond of timing precision for this particular pulsar. This is 22415236. And with all this, we are able to measure the dispersion measure with very high precision of few parts in million. So this is an order of magnitude better than what is currently achievable with any other telescope at any other frequencies. So coming to the ISM effects, so there are more. The interference of the scattered wavefront can produce the intensity modulations in frequency and time, or they can also give rise to a scattered broadened pulse depending on the delays. So the width of the scattered pulse varies as frequency to the power -4, whereas the scattering screen or the scattering angle varies as frequency to the power -2. So the combination of this along with dispersion gives rise to the frequency dependent dispersion measure. So this is a very new and theoretical concept. So basically at low frequencies, you measure the different DM as compared to what you measure at higher frequencies. Because low frequencies, the scattering angle is different. So the ray path travels a slightly different way. So therefore they track different number of electrons and therefore different DM and different frequencies. So this is the ideal case, but however, the ISM is not always ideal, so you can't imagine like what kind of stuff is going on there. So till now, this is a very important effect, and all the PTA experiments are adopting the wideband instrumentation for the PTA experiments, and tracking this effect is very important. Until now, there is very limited observational evidence for this effect. The only one is at a very limited observing range from like 50 to 200 megahertz, and it was done on a normal pulsar, which is a separate class from millisecond pulsar, which are used for the PT experiments. So this motivated me to take a multi-telescope observing campaign. Again, my paintings. So we contemporaneously observed this target from 80 megahertz to 4 gigahertz. So it's a huge frequency range. And so before we delve into the frequency dependent, there are a couple of other things which we need to account. One is the temporal variations in DM, because the pulsar, ISM, and the observer are moving relative to each other. So how we tackle that? We carefully planned our observations, and all the 3 telescopes were staring at my target within the 24-hour window. So we can tick that. Another thing is profile evolution with frequency. Because we are observing the pulsar over wider frequencies, the profile evolution tends to vary, and it is quite dramatic for millisecond pulsars. But luckily for 20 to 41, this is not the case. The profile looks simpler, and it is almost same from 80 megahertz to 4 gigahertz. And so we can tick the second point. Next is orbital DM variations. Most of the millisecond pulsars are in a binary. So sometimes the binary system forms the eclipse, or sometimes the companion winds interacts with the pulsar signal. That can give rise to the excess, some addition to the DM measurements. So this 20 to 41 is also in a 3.5 hour binary with a low mass companion. But it was very important for us to measure that if there is any DM variations over the orbit, so that we can completely understand the frequency dependence of DM. But we have one limitation. The VCS, the MW VCS can only record for 90 minutes. And this pulsar is in a 3.5 hour orbit. So how we did the full orbit? We split it the 90-minute recording time into 10 minutes of small observing chunks, and then in order to cover the full range from like 0 to 3.5 hour. And we use the picket fence mode in order to cover the larger frequencies, so that we can measure the DM with high precision. And it was a complicated process, but I will just show you the results. So here are the DM measurements. So 0 to 1 is the full 0 to 3.5 hour of the orbit. And you can see the DM measurements. So they are pretty much same, but you can see a small excess at the pulse phase of 0.4. This is very small, but we can measure it because of the low frequencies are sensitive. And this can still induce 110 nanosecond of delay in the timing frequencies if it is not accounted for. So, but the thing is that we can measure it, and we know how much it is. So we can say that, okay, tick, we know that how much it can contribute. So now we can go to the frequency dependent of DM. Accounting for all those things, when we measure the DM at all the different frequencies, you can see that they vary a lot. The DM at low frequencies at higher than the DM what we measured at, so the DM we measure at low frequencies is higher than the DM measured at higher frequencies. And this DM and at low frequencies, I can show you that there are error bars, but the measurements are very precise. Therefore, the error bars are very small. So this is just a zoomed in version. And this DM variation depends on the frequency lever which we are using. So it varies, like what frequencies we are using to measure our DM. And but another thing is that for this frequency dependent variations, we can do a fitting. So we can scale how much that DM is varying from one frequency to other. And we found that it varies on an average of 3.8, u to the power minus 3.8. And we have seen this consistently with all three our observations, and also for another pulsar, which I'm not showing here, but for another target as well. So in summary, I can say that at low frequencies, we can make very high precision DM measurements. And we did a very careful, dedicated observing campaign in order to investigate this frequency-dependent DM. And we saw this effect consistently at 3 different epochs for this pulsar and also for 2145, which is another pulsar. And if this is not accounted for, this can induce a timing delay at higher at the timing frequencies. But another thing is that we can scale this effect, but how much that scaling is varying from different targets, and what is the magnitude of this effect for different targets in the PTA sample is still an open question and need to be investigated further. Okay, that's it. Thank you.
Wonderful. Thanks very much. Right. So there's some very nice congratulations on Slack about your artwork. It's wonderful. I'd like to contribute to those congratulations as well.
Thank you.
Let's see. So a question from Mawson, who asks, does the relative velocity between us and the pulsar cause the DM to change as well? And if so, does the frequency-dependent multipath propagation dominate over that effect?
Basically, that multipath propagation is also changing because of the ISM and all these things are moving relative to each other. So it is not dominating. Sometimes we can see it has like it varies in the positive way, or sometimes it varies in the negative way. So it's not dominating, but it is varying with time.
Okay, great. Let's see. Yep, more congratulations on your art, and congratulations. Yeah. I just wanted to also, one more question here from Danica Scott, who also asks, is the magnitude of the delta DM for the pulsar expected to be typical of all transients with measurable DMs? And do you expect it to scale with scattering as well?
It is not exactly how the scattering varies. Scattering varies as Newton power -4. So, sorry, Newton power -2, the scattering angle. And what we measured on average is -3.8. So it is quite similar to how the scattering is doing, but we cannot say that this is the case for all the pulsars. So it can vary for different pulsars. It can vary with time because the line of sight maybe completely change after many years, after few years. So it needs to be tracked. The thing is that we can now measure it. So we need to be continuously tracked with like all the observations.
Yeah, right. And I think the first part was about whether the magnitude, the very small magnitude of the delta DM was expected to be typical for other sources that also show a measurable DM. Delta DM, I guess.
The delta DM for the frequency dependent or for
I think so. I think so. Yeah.
I didn't actually get the question properly.
Yeah, I'm not sure. Maybe you can follow up on Slack afterwards as well, sure, in case it's not clear. Yeah. But I guess maybe I'll ask a question. Is there any questions in the room actually, or on one of the hubs? I'll ask a question too, which is because you just mentioned that over time there could be temporal changes in this effect. I'm just wondering if this particular pulsar, maybe I missed it. Does this particular pulsar have a proper motion, a substantial proper motion, and does that contribute to?
All the pulsars have, because when they born, they got a kick, and they are like few hundreds of kilometers per second. So, and it also varies for different pulsars. For this particular one, it is like roughly 100 kilometers per second.
Mm-hmm. So it's probing different parts of the ISM as it goes along.
Yes. Yeah.
Okay. Okay, and I think this will be the last question from Mark Drouart. Are these issues enough to cause problems with gravitational wave detection? That's probably the right question to wrap up with.
Yes, definitely, because if we cannot account for these things, they can induce a few hundreds of nanoseconds of delay in the timing data. And eventually what PTAs are after is to achieve the precision of 100 to 200 nanoseconds. So if the delays or the noise contribution is more than 100 to 200 nanoseconds, eventually, yes, they can just cover up the gravitational waves and you will not be able to find them.
Right, okay. Okay, great. Well, let me recommend that you go back into Slack and see all the congratulations and also answer that one question that may not have been clear. And thanks very much again.
Thank you.
See you in all the And that wraps things up for today, I think. So we'll see you again tomorrow.